Hello, hello, hello. Today we're going to do problem 2458, height of binary tree after subtree removal queries. This is a Leetcode hard and it has 311 likes. And just like I just liked this Leetcode problem, I'd suggest that you like this video and subscribe to my channel because I post Leetcode solutions for new problems every single day. Okay. I didn't know that would happen. Okay. Let's get right into the problem. So you're given the root of a binary tree with n nodes. Each node is assigned a unique value from 1 to n, okay? So there's a unique way to reference each node in this tree. You're also given an array queries of size m. You have to perform m independent queries on the tree where the ith query you do the following. Remove the subtree rooted at the node with value queries I from the tree. It is guaranteed that queries I will not be equal to the value of the root. Return an array answer of size m where answer I is the height of the tree after performing the ith query. Okay, the queries are independent, so the tree returns to its initial state after each query. Okay, so you have a tree, you process the query, you remove that entire subtree, look at its height, and that's the answer for that query. After that operation's done, you then return the remove subtree, get back to the initial state of the tree, and then do that operation again for subsequent queries. Okay, the height of a tree is the number of edges, the longest simple path from root to some other tree, right? So this tree, for example, has height 1, 2, 3. 1, 2, 3. And if you remove 4, this tree has height 1, 2 because this is the resulting subtree. Okay, let's look at this example. Seems a little more, well, let's look at the constraints actually. Okay, so n is 10 to the 5 and m is 10 to the 4. So the easiest solution would be big O, would be big O of n times m, right? Because we can find the height of any n size tree in n time, and there are m operations, right? So essentially what you would do is take a tree, remove the subtree, that's a constant operation, so you just like maybe set information in that subtree node to 0, so you know when you're traversing the tree that you should return if you reach this node. Essentially, you remove a node from a subtree that you're querying, find its height, save it, put the information back, and then do that for every single query, right? So that's going to take n time. Each time you try to find the height of the resulting subtree after a query, that's going to take n time, and there's m such times that you have to do that, so that's O of n times m operations. So I don't think that's going to be efficient enough because this is 10 to the 5 and this is 10 to the 4, right? So we're going to be looking at, oh shoot, this again. Force quit. Okay, so we're going to be looking at what? We're going to be looking at n equals 10 to the 5, right? And m equals 10 to the 4. So that's going to be n times m 10 to the 9 operations. That's probably going to be way too slow. So we need to think about a different way of doing this such that we don't have an O of n times m runtime. Okay, so let's just draw this example and play around with it a little bit and see if we can use our intuition to find something that's a bit faster. Okay, so we have 5, 8, 9, 2, 1, 3, 7, 4, 6. Now the values of these nodes don't really matter, right? They're just unique. Okay, so Okay, so 589213746. So if we want to remove the subtree rooted at 3, right, the max height is still this length here, which is 3. Right? If we want to remove the subtree rooted at 2, right, well then this is no longer the max height because this tree is gone. So now the max height is 2 going this way. All right, information's 2, 3, 2 going forward. So it seems like if we took some information about the heights of each subtree, we may be able to pre-process information relating to each query, right? Because like we can look at the height of each subtree, and maybe from that we can figure out like, okay, if the height of the subtree is this and it's removed, then the max path would be this much less because this is the height of this selected subtree, right? Something like that. So let's go ahead and do that. So the height of these subtrees are 0, right? All the leaves have 0 height subtrees. The height of this subtree is 1. The height of this subtree is 2, right? Because we'll go down this path. Because we're talking about max height, right? The height of this subtree is 1. The height of this subtree is 3. Okay. Now, then what does that mean for the consequence if a node is removed, right? Well, if we removed 8, for example, the max path is here, right? So, how are we going to do this? Okay, I think I have an idea. So if you get to any level, like let's say we're looking at this level here, right? So let's look at this in terms of levels. Like this is level equals 0, and this is level equals 1. I mean by like this whole area, right? And level equals 2, and level equals 3. Now, why I'm trying to do that is that since we're talking about the length of this tree, right? At any level, the length of the tree is at least that level, right? Because if I get down to like here, or let's look at level 1, right? We're looking at level 1. So since this node is removed at this level, the length of the resulting tree is then the max subtree at another level plus sorry, Siri's trying to stop, Siri. I guess the idea is if you're at a certain level, right? Like you're at this level here. If you're trying to find the max subtree that doesn't include 8, well, that's equivalent to removing everything at this level, right? So then you can just add the other trees at the same level, and whichever one is the max will be the max subtree for this system. So let me try to draw a more general example, and maybe it'll make a little bit more sense. And my freaking thing died. I guess the idea why this is charging let's just first do the finding the length of each subtree. So we'll run DFS on a node. We'll call it root. Okay. And we'll make a dictionary. We'll call it height. So that'll be the height of the subtree. We'll make it a default dict because we don't really know what n is. We just know that there's n nodes. So the default value will then be lambda 0. And if not root, so we've found a child that doesn't exist, we just return 0. Otherwise, the height of this root, now since each root is unique, we can just reference the root.val. The height equals, well, 1, because you're one tree, right? Plus the max of our neighbor. So we have root.left, the max of DFS, right? So find the max height tree of root.left and the max height tree of root.right. Right, and then at the end, you just return height at root.val. And then let's run DFS at the root. And then just for testing, we'll print the height. So we should see, right, this resulting tree. Come on. Okay, so we should see this resulting tree in our system, right? So we have 2 has height 1, 2 has height 1, 3 has height 2, 3 has height 2, 3 has height 2, no. 6 has height 1. Oh, I think it's referencing this example. Okay, so let's change. Yeah, so let's change the input to this because that was the example we were working with. All right, let's look at that again. Sorry. So 4 has height 1, 6 has height 1, 2 has height 1, 8 has height 3. All right, so everything's getting over-referenced by 1. So maybe we should... Apparently I can't do simple things. We make that -1, and then everything will get propagated up 1. Okay, 4 has height 0, 6 has height 0, 2 has height 1, 1 has height 0, 8 has height 2, right? That's more so what we were looking for here, right? 8 has height 2, 3 has height 0, 7 has height 0, 9 has height 1, 5 has height 3. Okay, so we're able to successfully get the heights of all these nodes. Now let's continue going down this path looking at this example. So if this is the root, let's okay, if this is the root and we want to find the maximum height if we remove this node, right? So if we remove this node, well, the maximum height would be, well, we've gotten down to this level, right? So this is level 1, 2, 3. So the max height would then be the maximum subtree at this level, not including this node, right? So if you removed this node here, right, you have level to get down to this path. So the max subtree getting here would be any node that exceeds this level going downwards. And that's the general idea of this problem, right? So if this tree is removed, then the only option you have are the trees going down this way. Now I'm trying to think if there's edge cases, right? Like, what if there's this system here? If you remove a node at this level, there is no other such subtree at this level to traverse. Okay, but since we're removing a node at this level, that must mean there's a node above this node at a level -1. So if we remove this node, then the longest path is just level, right? Because if you can remove a node, that must mean it has a parent node. And if you remove a node at a certain level, that must mean there's a node at a level, at a previous level. Right, so when we remove this node, that means we consider the level above and the size of the subtrees at all subsequent levels. The size of all the subsequent subtrees at the same level. Okay? And that's probably the best that I can explain it. Apologize. So we got this height array. So what we're going to do then in this problem, and maybe this will help, is we're going to run BFS on this system, and we're going to look at each level. And when we look at this level, we're going to say, what's the max subtree at this level without 8? And then it'll look at this tree here and say, oh, well, without this, the max subtree is here, and that's length, well, the level is 1, plus the size of the subtree, which is 1, which equals 2. And then it'll do the same thing when it looks at this node, right? It'll look at this node and say, well, the max subtree, not including this system, at the same level is here, and that is 2 plus 1, level 1, 3. All right, so let's go ahead and get right into it. So we're going to create a queue since we're doing BFS. So I'll make a standard BFS approach, and then we'll integrate in the other part. So we're doing BFS queue equals child for node in queue for child in node.left, node.right, if child. All right, so that's a standard version of BFS traversal. So how do we process things? Well, what we want to do, let's say we had a system of nodes again. So I don't know what this tree looks like, so I'm just kind of making it like a cloud, because we're going to look at nodes at each level, right? So imagine that this thing had height 8, 7, and 4. Okay? So if I remove this node here, then the max subtree will be this one here, right? Because this one has size 8. So at this level, the max subtree is at size 8. So it'll be whatever the level is here. So we have level going down plus 8. If I remove this one here, well, then I'm removing the largest one. So now the max path is whatever the level is, plus this path was 7. So for any size level, you only need to keep the two largest subpaths, right? Because if you're erasing the largest subpath, you pick the second largest such path. And if you erase any other one, you only you always choose the longest subpath, right? So if this thing had, if there were additional nodes here at the same level, right? For all of these nodes, let's say they were all leaves. If all of these nodes were leaves, right? For this node, what would be the optimal path? If you erased it, 8. For this one, 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 8. The only time you choose something different is when you erase 8. So when I erase 8, I choose the 7 path. So I only need to keep information about the two largest such height trees, right? Where 4 is the height of this tree, and 8 is the height of this tree, and 7 is the height of this tree. Okay. So what we can do is we can say, well, let's keep the two largest nodes, U and V. So we'll use heap Q. Now you might say, whoa, this is inefficient. But since we're only keeping the two largest, this is a linear time operation. And we already have to do a linear time operation to get each child. So it's just doing the same sort of operation twice. So we're going to take the two largest, right, because we only need the two largest, since we'll always choose the largest one unless we're erasing the largest one, then we'll choose the second largest one. The two largest of our Q, where the key is lambda for the node, the height of the node at val, right, because we keep node vals. So then we'll have U and V. And then for each node in Q, we're going to create a new array called removed height, default dict 0, lambda 0. So the removed height at this node is what? Remember, everything inside the queue, since we're doing BFS, is at the same level, right? So everything inside the queue will be the nodes. Anything inside the queue will be one of these nodes, right? So how are we going to do this? So the removed height at the node, let's do val, is, well, it would be level. So maybe we should have a level variable in here too that we add every time so we know which level we're at. Maybe it should be negative 1, I think, actually. Sorry, negative 1. So it'd be the level plus, well, if it was the, we add the height of the largest one, which is U, if u.val doesn't equal node.val. Otherwise, we add the height of v.val if u.val does equal node.val, right? So I'm saying basically we always add the level. If u.val, so u is the largest one, so if we're not the largest node that we're removing, then we always prefer to remove the largest node, right? If it's not the largest node that we're removing, we always prefer the length of the largest node, right? If it's, so that's what this is basically saying, right? If we're not the node we're looking at, right? The node we're looking at, so we'll call this node, and this is U, and this is V, right? Because U is the largest, V is the second largest. If the node we're looking at is not the largest node, then when we remove this node, we'll choose the path of the largest node, right? So if u.val is not node.val, is not node.val true, then we're going to add the height of U. Otherwise, if it is the node of view, right? So if we're looking at this node now, well, then that's the one we're removing, so we can't add in its height. So we add in the height of vval, right? Because the height of vval is the second largest height in this tree. Okay, and that's pretty much the solution. So at the end, you just return for each query, you do removed height of query for query in queries. Queries. Apparently I can't spell. Queries. Okay. Now there might be a few bugs in here. That's okay. Okay, so not enough large values to impact. So if the size of the queue is 1, then there is no 2 neighbors to look at, right? Like in this example, when we remove 5, all we have at this level is 5. So what we could do is at every level, we could consider a dummy variable with value -1. And we could just always consider that variable when we do this calculation so that there's always at least 2 things to consider. And that dummy variable has length 0, so that will just make this flow better. Okay, so it seems like everything is off by 1. So maybe level should start at 0. Okay, that looks good to me. There's a standard out. Why is there a standard out? Let's just make this a little bit prettier. All right, because we have a lot of stuff that could go on one line. All right. It's all about making things end up on one line. Same with queue and level. All right. And then we'll expand this out so you can really see how short this is. All right, and then here, actually, let's go. Let's see what happens. All right, so I messed up somewhere. What's going on? Thinking that the height of the dummy might need to be -1. So the dummy has value -1. We'll just call it dummy now. Because if there's nothing, the height is -1 in the tree. So that's what my intuition is telling me here. All right, cool. All right, because if there's not root, the value is -1. A dummy is basically a none value, which is what this is. So then it makes sense that it should be -1. So maybe this height array could be a -1. And that would fix that. All right, let's try that. Just to save a few lines, you know, it's all about saving lines. And there you go. There's your really compact 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 line solution. All right, guys, I apologize that my explanation wasn't great. This is a very difficult problem, but I'm glad I was able to help. Thanks.